Okay, if that's not corny enough for you, I don't know what is. But here we go. We're going to talk about forces and motion this unit. And to start it all off, we're going to talk about none other than Star Wars, because that is where the Force originated, right? So we've got our big Death Star that's going to wipe out our population of the Rebel base, and then Luke is going to do his best to try to destroy the Death Star. And as he's about to take that final shot, he is told to use the Force. Use the Force to blow up that Death Star. So is that the Force we're going to be talking about? No, not really. But that Force was important then, and it's important now. And so let's get into what a Force really is. So here you'll see a definition of a force. Anything where you have a situation where you have a push or a pull. Sometimes you can actually feel the force touch you, like if somebody bumps you while you're walking through the hall, or if somebody pushes against a door, or as you slide across the table, you can feel the friction force between you and the table. So some forces are contact forces. We can feel them. Other forces, we know they exist because we can measure their effects, but we don't really see them actually happening, but we see their effects. Like gravity, the force of gravity, magnetic forces, electrical forces. So there's lots of different kinds of forces. But one of the things that they all have in common is that we can measure them as a push or a pull on objects. And we measure them in units called newtons. And we know that it takes forces to produce an acceleration. In the 1700s, Newton established there are three fundamental principles which were later deemed as laws about how objects move or what affects their motion. His first law is something you probably remember. It's sometimes also called the law of inertia. It talks about how an object that's at rest will stay at rest, or an object that's in motion will stay in motion. And so here you see Jabba the Hutt. Very, very large object. Has lots of mass. So if he's sitting still, he's going to have lots of inertia. It's going to be hard to make him move. His tendency is to stay where he is, unless another force acts upon him. An unbalanced force. Because you can push on Jabba the Hutt, but he's huge. He's not going anywhere unless you're able to overcome the forces that keep him in that place. Another way to look at Newton's first law of inertia is, well, what if you're on a racer and you're traveling through the woods? Well, you're in motion, and you will stay in motion unless another force acts upon you, such as running into a tree, or the force of gravity, or air resistance to slow you down. So in either case, inertia is the tendency of an object to continue doing whatever it's doing. So Jabba the Hutt will continue to sit because he has lots of mass, and if he did start moving, it would be hard to stop him. This racer is already in motion, so it's going to take another force to affect its motion. Newton's second law is where he actually attached a mathematical relationship to how things might move. So as stated before, it will take an unbalanced force to cause an object to change its motion, to change its velocity, because that's what acceleration is, a change in velocity. Objects tend to resist this change. We learned in the first slide that inertia means to continue doing whatever you're doing, so they want to keep doing what they're doing, so it's going to take a force to change their motion, and that force can be calculated. And it does depend on the mass of an object, the inertia of the object. The more mass something has, the harder it will be to either get it moving or to stop it while it is moving. And since we said that forces tend to occur in pairs, we call this F net because there's usually multiple forces acting on an object. And when we put all those forces together, We call that the net force. So let's look at an application here in action. Oh, and by the way, this formula, it might be something that you might want to record definitely in your notes and highlight. You will be asked to use this. And you can see that the acceleration in this formula is a concept that we've discussed in the past. So we will definitely go back to looking at how velocity changes over a certain time and how a force can cause that change to occur. So here we have two objects of very different mass. We have the Empire Death Star and we have the Empire Star Cruiser. So when we look at our questions here, which object requires more force to get moving when they're both at rest? Well, this seems pretty much like a simple answer. The one that has more mass is probably going to take more force to get moving. And there's no probably about it. The more mass you have at rest, the harder it's going to be, or the more force you're going to have to apply to get it moving. So that Death Star is going to take way more force to get moving than the Starship. Well, now let's just suppose that they're both in motion. It says which object requires more force to keep moving once they're set in motion in space? If you said the Death Star, you're wrong. If you said the Starship, you're also wrong. Because once you're set in motion and there are no other forces acting on you, such as in space, where you have no air resistance and the gravitational effects of other things is basically almost nothing, once you set something in motion, its inertia will keep it moving without any additional forces needing to be supplied. Now, if it were to come in contact with something else, then we got a whole different story. But the way the question reads is, which object requires more force to keep moving once it's set in motion? Well, once we get it in motion, we don't have to apply any more forces. Now, which object would take more force to stop it once it's in motion? Now you're talking the Death Star. It would definitely take a whole lot more force to stop that sucker once it gets moving. So Newton's first law dealt with the inertia of objects. Newton's second law deals with the relationship between the amount of force needed to make an object move based on the mass of the object. And Newton's third law deals with once those forces are applied, what might be some of the effects? So hopefully you see the familiarity in Newton's third law. For every action force, there is a reaction force that's not only equal in the strength, but it's opposite in direction. So since direction is important, force is a vector quantity. And strength means magnitude. So a force has a magnitude and a direction. That's what makes it a vector quantity. So you can push to the right, and that might be a positive force, and then something can push back to the left, and that might be a negative force. So forces will have a positive value or a negative value based on whether their direction might be up or down or left or right. So if we think about Newton's third law, as this stormtrooper is firing his gun, the bullets will go forward, but the rifle will recoil backwards. So the force causes the bullet to go forward, but that same force causes the rifle to go backwards. Well, who moves more? The bullet does, of course. The bullet has a much smaller mass, so it's going to have a much greater acceleration. The same force applied to the gun makes the gun go backwards, but because the gun has more mass, it's not going to accelerate nearly to the degree that the bullet does. Same thing with our Death Star and our planet there. Although they look like they're different sizes, I'm pretty sure that the planet has got more mass. And the Death Star also has a lot of mass. But here's the weird thing. The force between the two is the same. When the planet pulls on the Death Star pulls on the planet. If the Death Star pulls with 1,000,000 newtons of force, the planet responds with 1,000,000 newtons of force. So Newton's third law basically states that the forces are not only equal in strength, but they're opposite in direction. So Newton's first, second, and third law help us to describe and explain the motion of objects. And this is the introduction to our unit. And we'll be delving more deeply into other concepts related to forces, such as air resistance, terminal velocity, and friction.